Okay, so good morning. So I'm going to discuss to you tutorial about the analysis of the bearing capacity for shallow foundation, specifically for spread footing. And as you are seeing it here in the slide in the screen, we're going to use the EUROCODE 7. We have 5 ultimate limit states. Basically, we're going to analyze using the strength or the structural and then ground strength verification for this analysis of shallow foundation. So in this limit state, you have these design approaches. You have in design approach 1, these combinations has two approaches, two combinations. You have A1, M1, and R1. And for combination 2, you have A2, M2, and R1. And for your design approach 2, you have A1, M1, and R2. And then for design approach 3, you have A asterisk, M2, and M3. A asterisk is dependent on your actions. It should be A1 if that is in consideration for the structural actions, and A2 for geotechnical actions. Alright, so as you see here, these are the partial factors. For example, you have A1. For permanent actions, you have these values, variable and accidental action, A1 and then A2. For M1, you have here all values are equal to 1, and then you have for M2, and then for the resistance, which is R1, you have here all values of 1. Okay, so in this limit state, we only consider R1. Okay, so let's proceed. So as we all know, just for a brief review, you have to consider the actions and effects here. You have your representative action, could be like the permanent or variable. Then you are going to multiply it with the design actions and come up with geotechnical analysis. Similarly with the material properties, divide it with the partial factors to come up with the design material properties. Go with the geotechnical analysis, and then you consider the relationship to verify the design effect of actions, that is E sub D, and then the resistance R sub D. That means if E sub D is less than or equal R sub D, then your analysis is satisfied. Alright, so for example, you have here a continuous footing. You have 1.8 meter in width, you have 0.5 in deep, and is founded at a depth of 0.75. The unit weight of the soil is 20 kilonewton cubic meter, and then cohesion is 30 kilopascal. The foundation is to carry a vertical line load of magnitude 50 kilonewton per meter run. So this is continuous footing or strip footing, so we consider in every meter. So this could be your analysis. You can calculate this one from the load of your footing or from the building that you are designing. Right? So which will act at a distance of 0.4 meter from the center line. That means you have a eccentricity of your design action. For example, if this is your footing, alright, so here's the center line, your load is here, and this is your eccentricity. In this case, you have a value of 0.4 meter. Now we take the weight of or the weight density of the concrete as 24 kilonewton cubic meter. We analyze the bearing capacity for the footing. You have factor of safety is equal to 3.0, and then check the EUROCODE 7 geo-limit state design approach number 1 by establishing the over design factor. That is, if your design effects is less than or equal the resistance. Okay, the material resistance. Okay, so as we say, you have this the footing, and actually your load is over here with an eccentricity of that is 0.4. Okay, so from the values, you have the self weight is equal to the thickness, which is 0.5 here, and then unit weight of concrete, and then 1.8 is the width. So you can get the self weight of the foundation in every meter. The weight of the soil on top of the foundation here is this one, This is the soil that is to be considered at the top of the foundation, like it is also a permanent load, and it is also unfavorable. Okay, so we calculate it here. You have 0.25. Since this is 0.75, this is 0.5, so this one is 0.25. Okay, so you have 0.25 times 20 unit weight of the soil, and then width, which is 1.8. So you can take the total weight of the foundation, the weight of the concrete, of the footing itself, and then the soil on top of it. So you have 30.6 kilonewton meter per run. Eccentricity of the bearing pressure. Where's this eccentricity of the bearing pressure? You have here. Okay. Here is the pressure. Your pressure could have like eccentricity over here. Okay. If it's not really acting on the center line, then it has an eccentricity. Alright, so let's calculate. You have here this formula, E. You have the load, which is 50, eccentricity is 0.4. Eccentricity of this load, which is this one. No, this one. Alright, and then again load, and then the weight of the footing. This is like the total load. Design actions, load from the building, and then the self-weight of the footing and the soil. So the eccentricity is 0.25. Now we can calculate the adjusted width of the footing. This is just B minus 2 is the formula. 2, and we have calculated eccentricity is 0.25. Okay, so taken from the table, these are given that the soil has an angle of sharing angle is equal to 0. From the table you can have these values. Now in calculating the bearing capacity, it should be net for the safe bearing capacity. Take note this formula of NQ minus 1. If you are going to substitute NQ, which is 1, so this becomes 1 minus 1, so this all becomes 0. NY is also 0, so this one is also 0. So we can just use this one. Since this is net, and we're calculating factor of safety, we're calculating safe bearing capacity, we divide here by factor of safety. Factor of safety is given to be 3, and then plus unit weight of the soil, and then the depth to the bottom of the footing. So that means we only need, actually you have SC, there should be IC here, but IC is equal to 1 since there is no inclination on the angle. SC is also equal to 1 because this is strip footing, so we just calculate DC. You just have to satisfy in the Meyer formula this function. If it's less than 1, Z over B is less than 1. Take note that the ground up to the base of the footing is like 0.75. Okay, B is 1.8, so it's less than 1. So calculating DC, we use this formula. That's why we have this. So it's 1.23. So you have substitute cohesion is 30, NC is 5.14, it's here. IC is 1, SC is 1, and then DC is 1.23. This one is Y, unit weight of the soil, and this is Z. So this would be your safe bearing capacity. You multiply it by B prime, or the adjusted width, which is 1.3, that becomes, you have 101.7 kilonewton meter per run. So this is the safe bearing load with a factor of safety equals to 3. Now, check the EUROCODE. According to the problem, we are to check with using the design approach 1. So in the design approach 1, there are 2 combinations. So you have here the first combination, A1, M1, and R1, and then the second one is A2, M2, and R1. First, we identify A1. A1 here, where is A1? This is 1.35 and 1.5. That's why you have here 1.35 and 1.5. Okay, and then M1, you have here, this one is 1 YCU, or the factor of safety for shear strength, and then factor of safety here for bearing is this one. These are the relevant factors. This is for M1 and this is for R1. You can check this one, but it's not necessary. Alright, so because your angle is also 0, okay, so it's not necessary, but you have to check it one by one in most of the cases. So you have here given this material, okay, the cohesion is equal to 30, uh, this value, the shear strength I should say, the shear strength is 30, and then you have here this value, this factor of safety. So that means you have this material. Okay. Now design actions. The total weight, which is 30.6, okay, and then multiply by factor of safety, which is 1.35, so you have this 41.3. And then the load, this is actually the weight of the footing, okay, weight of the foundation, which we calculated earlier. You can just go back. So this is the load of the strip footing, and then multiplied by the factor of safety, so you have 67.5. Again, these are these values, okay, 30.6, this is the weight of the footing, calculated earlier. Okay, so the total vertical force, 41.3 and 67.5, these are all factored already. Where is this 41.3, this is 41.3, and this is 67.5. So with this formula, you have the total P, which is 67.5, eccentricity is 0.4, eccentricity on the load, on the footing, and then the load, and then the weight of the foundation, the footing. So you have this eccentricity. Using this formula, B minus 2E, eccentricity is this one, it will give us 1.3. Now, how are we going to calculate the resistance? The resistance, which is the bearing capacity of the soil, using this formula. Okay. Again, this is strip footing. The formula for strip footing is this one. Okay. Now, in this case, Ny is equal to 0, so we can just cancel this one. So we can just use these two factors. Okay. SC, there should also be here SQ actually. This is, there should be DC here. Okay. But alright, and then okay, so your SC here is 1, so you can just neglect SC, and then IC, because we are using Meyerhof, okay, Meyerhof formula. IC is equal to 1 because there's no inclination. Okay, so we just use CU 30 and C. You can just disregard also here DC. Okay, just disregard here DC. So you have 30, 5.14, which is NC, and then SC is equal to 1. NQ is 1 also. This is 1. Unit weight of the soil, which is 20. Z is equal to 0.75. So this will be your ultimate bearing capacity. Your ultimate bearing capacity in kilopascal, when you divide it by width, which is 1.3, this will be your ultimate bearing capacity per meter. That becomes your resistance if you're going to divide it with the factor of safety. This is 220. Earlier in our calculation, the design effects, which is that one, 108. Okay, this is the design effects. We compare it with the resistance, which is 220. So that means this is greater than 1, and we can conclude that this is satisfied. Okay, the load, the design load, is greater than is smaller than the resistance. So the resistance is the capacity to carry the load acting on it. All right, so this combination is satisfied. Now the same through with combination 2. How it differs to combination 1 is their factors, because for combination 2 their factors is all this one, right, and the M2 is this one. Okay, so getting these factors, you have this one, okay, 1 and then 1.3, and then you have here for which is 1.4, and then all here is 1. Okay, factor for shear strength, and then for the resistance, bearing resistance, which is 1. Okay, we can calculate. This is given, the shearing strength, divide by 1.4, which is this. So this will be your factored value. Now the load, which is 30.6, okay, but this is 1. The load is 50, and this is 1, so that becomes your 50. You get the total design actions. This FD is the design actions of 80.1. Now similarly with the previous one, we can calculate the eccentricity. Alright, and then the ultimate bearing capacity, again, only for CU, NC, and SC. We don't consider DC and IC. Only SC is where we only consider shape factor. Okay, you multiply by the adjusted the width, so we have this QU. Now we get the value of the factor of safety for the resistance. Okay, this is how we calculate earlier, just to show the loads, weight of the footing. Okay, this is the bearing capacity, the eccentricity, the adjusted bearing capacity. Okay, we calculated already the ultimate bearing capacity. Okay, the actual bearing capacity for, or the resistance. Now considering its partial factor of safety, again the partial factor of safety is equal to 1, so you have here is our resistance. Again, your design actions, FD, is smaller than the resistance, so this is satisfied. In other words, the over design factor is just resistance over the design actions is 2.002, which is greater than 1. Compare it with combination 1. Combination 1 as a design 2.03. Okay, so this one has bigger factor. Okay, so the much more safer, much safe. Combination 1 is much safe. Alright, so we can use, in this case, if you are going to choose, we use in the analysis this combination 1. Okay, so that's all for this one, using safe bearing capacity and then the EUROCODE 7. So that's all, and see you in the next video tutorial. Thank you.